Okay, hey there everybody. I am Shivani. I am with GoEngineer. I am a simulation specialist out of our Houston office, and this video is on tank sloshing in SOLIDWORKS Flow Simulation. So what I'd like you to do is consider first, what is tank sloshing? We're going to kind of overarching answer this question. How do I analyze it, and what do I need to know about it? What do I need to know in advance to even be able to set this up? So, I want you to consider a partially filled tanker in a braking condition. The liquid inside its tank will continue to move forward, slamming into the walls, like we see here, then sloshing back and forth in waves. So it begs questions like, how much force did that just apply on the tank in the X direction? Will it cause a dangerous pitching moment? Or potentially, how long will the waves last? Are they going to dissipate out faster in certain baffle configurations or not? What is the best baffle configuration? I am out of Houston, so many of my customers are in the energy sector and do model baffles for situations exactly like this. So using SolidWorks, we are going to use some predefined baffle designs, and then using SolidWorks Flow Simulation, will determine which design is the best. Now, why am I doing that? Let's take a look at physics that I need to be aware of before I'm running a simulation study or picking a simulation program, right? These are common physical effects that I might need to understand about water. So droplet meniscus, gas and liquid interaction, the fluid flow, absorbing heat, evaporation, boiling, basically phase change. If I'm talking about fluid in a tanker, it's moving pretty fast. It's the volume of the fluid really driving the motion. Droplets and small details like the meniscus are not affecting the overall flow. So that's a concept of surface tension, and we don't need to worry about it. We can leave that math out. Also, phase change can be ignored. We're not really focusing on heat in this tanker right now, so cooling down or heating up. So we're kind of focusing just on the interface of liquid and gas and then how everything is flowing, which makes this a really good use case for flow simulation. Okay? All right. And another big thing, we get results within a few hours rather than a few days. You can quickly get results when you're using an integrated software like this. So what did we do? On the top left-hand corner, you should be able to see the baseline design. It's just a 6-foot tank or a 12-foot long tank. It's 3-foot diameter wide or in diameter. And I've called that design 0 here. And then from here, I built out different baffle designs. In the configuration tab, let's go find SOLIDWORKS. You'll see that I set up 3 different configurations here. I did that intentionally so that I could quickly copy studies over in the flow simulation projects and then compare results easily as well. All 3 of these designs have a similar arrangement of the baffles. You'll see I have 2 long plates, and then I have 3 cross-sectional plates. But the cutouts are varying in each one. You'll see design 1 has an open surface area of about 1830. It's more of a single channel. It's my leading towards the idea of like a suppressor on a gun. So mostly a single channel that the fluid is flowing through. The second option was leading more towards a perforated plate, so smaller, similarly shaped holes that are more spread out. And then the third design was more of a combination. Cool. So those are the 3 that I came up with. I didn't take these from any customer, so they're not, industry standards, but I just came up with this. So we're going to see how they all compare against each other. We're kind of dealing with a meniscus layer, so let's jump into the general settings. And I'm dealing with, not a meniscus, but immiscible. So we have 2 immiscible fluids, our air and our water, and that is what is going to be involved in that tank there. They are treated as homogeneous as well. The interface is called a free surface. That's a name used by SOLIDWORKS and generally to refer to the fluid interaction, that layer in between. And it's also what flow simulation uses to refer to the calculation method. You see that here. Also, the tank is considered to be positioned horizontally like this, where the center of the Earth is in the negative y direction. So we see that 1g loading there. but I'm also simulating a braking condition. And so I am simulating that with a acceleration curve in the positive x direction. You see that dependency option there. So it's created using dependencies. So the G load is applied over 4 seconds. See that curve here? It's peaking at about half a G. That's what this value is. And that's a common G loading for an average driving situation on the driver. The analysis overall is run for 10 seconds. So I can watch the loads under braking and then the after effects of the wave to see how fast that dissipates. Awesome. So gravity, free surface. Otherwise, we have default wall conditions, default initial conditions, and my initial fluid in the tank is air. All right. Now for all 3 designs, or 4 designs, I have an initial fluid of water here at the bottom of my tank. To set that up in Flow Sim, I need to create an initial condition. So you're going to go find initial conditions in your tree or in your menu and add one. You're going to select your solid body or your part file representing your volume of water. Be sure to select disable solid components and then come here to this drop down and pick which fluid you want it to be. From here you can see that I left default thermodynamic parameters and zeros on my velocities. That is because at the initial start time, the water is moving 0 inches per second relative to the velocity of the tank, right? So there's no initial velocity here or initial impulse load. If I was trying to represent a situation more like slamming into a brick wall instantaneously, it might make more sense to actually have a velocity input here. That is not this case. So now I have a volume of water sitting here at the bottom, and then I have my air on top. Now, since this is an internal analysis with no flow rates into or exiting the tank, I have learned it is a good practice to create a fluid subdomain. So again, you're going to find that in your tree or in your menu. You're going to right click on your tank, select other, and in my case, you're trying to click an inside face. It could be a face of the water or a face of the tank itself. Select it like so, and then make sure it's set to an immiscible mixture with air and water. Okay? I'm going to go ahead and cancel out of that. It's just a step that I would do. All right, that generally completes the analysis setup. I'm going to talk a little bit more about extra options, things like goals and mesh. So in my goals, these are the things that I am choosing to track because it matters most to my design. For a tank braking, I mentioned a few questions at the beginning of the webinar. So I was saying I cared about force in the direction of braking, so the x direction. I cared about pitching moment, so that's about the z-axis, so torque about the z-axis. And then I cared about just the overall turbulent energy. It was a way for me to measure how much waves still needed to dissipate, so I captured bulk average turbulent energy. You'll see I have other goals in this list, things like forces in the other directions or moments in the other directions. Absolutely an option for you to pick. You'll see I also have a few things up here at the top. These are more sanity checks. They aren't necessary for the results I want to look at the end, but while it's solving, I do like to look at these things. It's a personal preference. It's, like I said, a sanity check. So velocity or pressure is one of my ways of sanity checking a free surface or really any analysis I'm running in Flow. And I'm just watching for weird pressures or velocities. So that's why I have this in here. And then I've got volume fraction of air and water. So this case, those are fixed volumes. I want to make sure those stay fixed, right? And that I didn't mix something up. In case you're brand new to Flow, these are global goals. That's what GG stands for. So it's measuring that over the entire 3D volume. Okay, so that was my goal setup. Let me get a little bit into meshing. And I'm going to hide this water so it's not in our way. So I didn't do anything crazy with mesh. You can see I did not do a local initial mesh or a localized area of mesh refinement. That is because it is important for me to kind of okay, so we're using the volume of fluid method. So for accurate answers, I need a good representation of the volume of the fluid, right? That just seems logical. If I have fluid cells that are too large, I'm not capturing that interface or that free surface very well, and so I'm getting a very blurry, strange kind of result. So it is recommended that you do refine anywhere that there's going to be a fluid interface. And for a tank like this, that sloshing could really be anywhere, so I'm talking about refining everything in that tank. This level 1 refinement, this is what I used for my comparison studies. It is still a little bit large, but it is fine-tuned enough to get me detailed answers and to converge on results and to quickly get me answers, more importantly, within an overnight solve scenario so that I can compare those within a day, right? If I then picked a final design and I wanted a more detailed set of results, I would bump up this refinement level to at least 2. You can go higher than that, of course, depending on how much RAM you have and solve time you want to dedicate. So how did I do this setup? I'm going to scroll up and go to this refining cells drop down. You can see here I slid over the refining fluid cell slider bar over to 1. So that's me showing the 1 level of refinement, or the 1 time smaller that I chose there for the entire fluid domain. And I can prove that out in my solutions or my results. Take a look at that mesh. There it is, that 1 level of refinement. Like I said, good for a comparison study. I would do something smaller for a final test result. Now, before I jump into the results, actually, there is some subtle things I did in the calculation control options. So let's go take a look at that. It's starting with thinking ahead on what kinds of results that I want, specifically animations over time. And I get that in this saving tab. So this is best tracked using the Transient Explorer. These can be heavy on file size, so be very careful of the results you're choosing to export. Immiscible is recommended, especially in a case like this with fixed fluids. What is not recommended is mass fraction. And I pulled that here to remind myself to tell you that. When you're dealing with a situation like this where you have 2 fluids with vastly different densities, if you have a small pocket of, or a small volume of air that just has a little bit of water in it, the density of that water, or the mass fraction of that water, overrides that cell and makes it look like there's a lot of water in that cell when there really isn't. So mass fraction can be misleading in free surface situations like this with a gas and a liquid. Okay? So what I would do normally, get the dot 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 here, is pick volume fraction if I wanted more of a distribution, and I would definitely do an immiscible choice. I have this mass fraction here. If we have some extra time at the end, I can show you a comparison. Okay. What else is in this calculation control option? So on the solving tab, you'll see I left the time step on auto. That is to keep this the most accurate. If I was troubleshooting or just really quickly trying to push a result out, I would likely make this a manual time step of a larger number, something like 0.01 seconds, potentially. I'm introducing error when I do that, but it helps me get to an answer quicker, so I can make design decisions. I'm not doing any automatic refinement. I don't want to increase my solve time. And on my finishing tab, you can see I have this running for 10 seconds of the tank time. Now I'm going to back up for a second and take an aside here and talk about batch runs for my 4 different designs and my personal recommendation on this. You'll see I have calculation time turned on here with 5 hours of calculation time chosen. This is you and me time, our real life time. By limiting this to 5 hours of solve time and running 2 projects simultaneously, I can get a majority of the way through all 4 calculations overnight. They might not all finish, but I can get a majority of the way through them. Thus, when I return in the next day in the morning, I have an idea of how each of the flows developed or are developing, and then I can make design changes or change my analysis and continue from there. What I would do is remember to go back into calculation control options, turn off calculation time, as a finishing condition. And then the next time I choose to run this, it's going to continue where it left off and complete the last hour or two, let's say, that it has to do. I love that about Flow, that you can continue where you left off rather than starting at the beginning. All right, so I have all that. Let's take a look at my results. With Transient Explorer active, I can create a cut plot. That's what I generally do. Cut plots, two-dimensional cross sections. I can only plot the results that I chose to save out in the Transient Explorer. You'll see that's immiscible water and mass fraction only. And I can play that to get an idea of what that fluid is doing over time. So it looks good. I can see a bit of splashing going on there. We want to fix a lot of that, don't we? But I'm able to get a really good idea of what's happening in this tank. And I can look at that at any cross section that I feel like. Now that's just a nice visual thing. Let's go compare that against all 4 of the tanks. When I look at this, it's not getting me too much information on which design is the best, but I can very easily see the 3 design choices there are definitely dissipating the energy or the waves far faster than no baffle design. Let's come back here. Just looking at visual results is not all that we do here. I'm going to go ahead and take a look at numerical results. And I'm going to show you how to do that with goal plots, because that is a very quick way to get results over time. So I'm going to go to my goal plots. I would choose which one I want to spit out. In this case, it's going to be torque. I make the x-axis physical time. Hit show. This is just a value at 10 seconds. That's not what I want. I want to see what's happening over time. So this is design 0. This is pitching moment, or torque about the z-axis over time. I can see it gets to about 70,000 inch-pounds in the worst case, and then starts damping out. I want to compare that against all the other designs. What you could do is export to Excel right from here, and then just choose to export all your other configurations or all your other exports. I have a faster way to spit that out into Excel, or to compare them even. I'm going to go to Results, Compare, and I already showed the results, but let me go here to Definition. What you do is you pick the plot that you want to compare. It could be numerical or it could be a visual result. You pick which projects you want to show. You hit Compare. That pulls the results from all the different studies, and then you get tabs that you can view like this. So here we are seeing that the torque value for design 1 appears to be the best. So very quick visual outputs there to base design decisions off of. From this choice, if you wanted to do more with this, you can, of course, extract this out to Excel. There's a button here. It's a right-click export. As you do that, it gets you columns of data for every single data point in these charts, if that's what you needed. Okay? I exported the common ones out, plotted them, and dropped them here. So here is force in the x direction, the braking direction. I can see that my no baffle design, is wobbling around, but all my 3 baffle designs are pretty even. We can see that hits pretty much the same value and then evens out the same value. So I've learned that it's good to have baffles, but not much else. I don't know which design is better. Here is the plot we just looked at. It is torque in the z, around the z-axis, or pitching moment. And like I said, we have design 1, that's the suppressor design, the single channel down the center. That seems to have the lowest torque and gets down to a low torque very fast. Interestingly, that combination design, design 3, that mixed the large channel in the center and the perforated plate holes on the side, it actually damps a lot faster than both of the other choices. I found that interesting. Maybe if I worked on that combination a little bit more, I could get the overall torque value low and damp faster than the others. So, I was kind of thinking back and forth on that. I'm leaning towards design 1, that's suppressor design. So I take a look at my last plot, which is the average turbulent energy in the entire system over time. A lot of my peaks are pretty similar, though overall, I am seeing design 1 still reach lower values here over that 10-second frame. So I'm feeling pretty confident on picking design 1 compared to the others. So ultimately, using SOLIDWORKS Flow Simulation, we're able to use both visual results and numerical results to make some really detailed design decisions on which baffle design was best. Thank you guys so much for attending. Please feel free to go to our YouTube page and check out any of our other pre-recorded webinars or reach out directly to us for one-on-one sessions. We are so happy to help you guys. Thanks for coming.